Hi, I'm Ruth Nagassa from Monash University in Australia, and on behalf of myself and my co-authors, Matthew Butler, Leona Holloway, Cagatay Goncu, and Kim Marriott, I'm presenting our paper on 3D building plans supporting navigation by people who are blind or have low vision in multi-storey buildings. I'd like to begin with an acknowledgement of country. Monash University recognises that its Australian campuses are located on unceded lands of the people of the Kulin Nations and pays its respects to the elders, past and present. Independent travel and navigation in new environments, in particular multi-level buildings, is a major challenge for people who are blind or have low vision. Orientation and mobility training, or O&M, is commonly used to prepare for travel in new environments. Tactile maps are an important part of this training. They serve as an introduction to the layout of an environment and help build a cognitive map prior to visiting. Tactile map presentations of multi-storey buildings generally present a tactile floor plan for each story as illustrated on the slide. This requires the reader to mentally merge the information on each graphic to understand the spatial relationships between each level. Although tactile maps are central to O&M training, such maps of multi-level environments have received little attention. More recently, 3D printed maps have been suggested as an alternative to traditional raised line maps, as shown on the previous slide. They offer an advantage over raised line graphics as they allow the direct representation of 3D objects, including representative icons, and are effective at conveying composition and spatial information. In this paper, we address the overarching research question: can 3D models of multi-storey buildings help people who are blind or have low vision build spatial understanding of such environments and construct an effective multi-level cognitive map? Previous work has highlighted end-user interest in maps of shopping centre areas. For this reason, we chose to 3D print floor plans of 3 fabricated local shopping centres. Through co-design with the blind colleague, we conducted a controlled study to evaluate the 3 designs. Our first design was a flat model in which each floor was presented separately and placed on a horizontal surface in front of the user. The second was a sliding model in which each floor could be slid to the side. And the third was a rotating model in which each of the floors were able to be rotated on a vertical rod. We used a within participant design with each participant using each of the conditions, flat, rotating, and sliding, with a different floor plan for each. The study was designed to address the following interlinked research questions. First, would 3D models of multi-level built environments be valuable in O&M training? Second, what kind of cognitive map do the models engender, and is this affected by model design? And last, how appealing and effective for spatial understanding are the models, and how is this affected by model design? So the study consisted of 7 parts and 2 breaks. We recruited 9 adults who were blind or have low vision to participate in the study, and the study procedure began with a questionnaire to evaluate participants' confidence in visiting unfamiliar buildings and their perception of the importance and difficulty of building a mental model. Next, we conducted a practice session to familiarize participants with the model and procedure. Participants were then given the opportunity to explore the model at their own pace. Once they were comfortable, we posed recall questions to assess the accuracy of their mental model. This was followed by spatial understanding tasks, such as planning a route that relied on cross-floor spatial understanding. Afterwards, we evaluated the usability and engagement of each design. Finally, we assessed user preference, perceived usefulness, and collected design feedback. So on to our findings. Only 1 participant self-reported a very high confidence in visiting new buildings, while others either had a low or neutral confidence. 8 of the 9 participants agreed or strongly agreed that it was important to them to have a mental model of the layout of an unfamiliar building before visiting. About half of the participants agreed they found it more difficult to build a mental model of the layout of a multi-storey building than that of a single story. After seeing each model, 8 of the 9 participants strongly agreed or agreed that pre-journey access to models such as these will make them feel more comfortable to visit a shopping centre. All participants agreed that there was a use for such models. This included buildings such as airports, office buildings, and libraries. So onto the mental model. Firstly, for all participants, vertical connectors served as landmarks and indicated points of cross-floor connection. Second, participants' ratings suggested it was easier to understand cross-floor relationships with the overlap designs. Third, there was some indication that the different presentations engendered different cognitive maps. Participants were more likely to develop a cognitive map of the building as a whole, rather than discrete floors with the overlap presentations. While we expect to see an increased accuracy in recall tasks for the overlap presentations, there was little difference between the presentation conditions. This suggests that despite any differences in the cognitive map engendered by the different presentation methods, functionally they encode equivalent information. So next, touch reading strategies. Interestingly, 6 of the 9 participants chose to overlap the floors of the flat presentation during exploration and spatial understanding tasks. With the overlap designs, however, participants frequently realigned the floors after having moved them for individual exploration, and used their hands to follow the escalators and lifts in order to establish the connection between floors. In Part 5, the procedure, participants would use the model to answer 2 route planning tasks and 1 corresponding point task. All participants were able to complete the route planning tasks on the first attempt. Furthermore, the perceived difficulty of completing these tasks was similar across all 3 presentations, with each receiving an average rating of easy in the single ease question scores. The average system usability score for all 3 was above average on the border of good and excellent. User engagement scores were high for all 3 presentation methods. Nonetheless, observation and participant comments suggested that the sliding and rotating models led to greater levels of enjoyment. The idea of fun was also indicated by 5 participants with a clear preference for the overlapping models. All 9 of the participants listed an overlapping presentation as their most preferred. Ultimately, it appeared one key aspect of both overlapping presentations was the ability to bring floors of focus in and out as needed. Lastly, it was clear that the design of the vertical connectors, being the escalators and lifts, were effective at conveying cross-floor connections. In conclusion, our study provides a rigorous evaluation of cognitive mapping and cross-floor spatial understanding using multi-level 3D maps. All 3 designs were found to be useful, usable, engaging, and effective in supporting cross-floor spatial knowledge. Our novel overlap designs demonstrated clear advantages over more traditional flat floor plans. The participants showed a strong preference for the overlap presentations, which were more effective in supporting cross-floor spatial knowledge. We believe that the availability of such maps will enable people who are blind or have low vision to navigate complex environments with more confidence and independence. Our exploration of the design space of 3D building plans provides a solid foundation for future development and research in this area, and we hope will encourage the provision in O&M training and availability in public spaces. Thank you for your attention.